Yeah, speed up the development and drive quality with the miniHIL. My name is Thomas Schütz. I'm CEO of PROTOS. We have the focus on development software tools, test tools, software architecture, and the like for embedded systems, especially model-based tools, code generators, formal verification, and so on. And I'm basically an aerospace engineer who likes embedded systems, embedded software, embedded architecture, and especially tools. Yeah, why are we doing what we're doing with the miniHIL? One of the biggest problems in development is that it's very expensive if you detect a bug late in the process. If you retest, for example, during implementation, let's say you make a unit test, you change the implementation after you detect a bug. It's relatively easy and fast, very fast in the process to rerun a unit test. You push a button and that's it. But the later you get into the process, the more expensive it becomes. So for example, a system test, that's a test you might only run every couple of weeks or maybe every couple of months, depending on your system test, depending on if it's automated or manually. But it's very late in the process usually, so you get a very slow response time, a very long response time, and then it's really expensive to retest, to find the bug and to retest the bug. And why it's even more expensive after the release, I guess I do not have to elaborate on that. So what we do with the miniHIL and our test systems is we bring the integration test and the system test to the desktop of the developer or to the continuous integration in order to speed up the testing process in the later test stages through automation, through code generation, and so on. So instead of waiting for a couple of weeks for a system test, you can run the system test after every commit. So after every couple of minutes or hours or something like that, you can run the system tests. So that's what we do with the miniHIL. Let's have a look from a different perspective. Let's have a look at the process, at the development process. Yeah, that's a typical development process for an embedded system. You start on an evaluation board, maybe. Then you commission your drivers, you program your hardware-related software components. So for example, motor controllers or bus protocols, something like that. I/O-related software components. And then you add the pure software components, for example, for the application logic, for error handling and things like that. You integrate everything into an application, and eventually you move to the real control unit, to your real microcontroller, or to your real ECU. The question is now, where do we test? Usually the tests are done in the early stages, mainly for software components, because they are easy to test with unit tests. Please do that. That's fast. That's easy to do. That's completely, it's easy to automate. So you run your software component tests as unit tests. And then later in the process, you might have a hardware-in-the-loop test system or a system test. So here are two problems. One problem is that you do not have a lot of coverage here in the early stages, because there are a lot of potential errors in the hardware-related software components and in the integration of all the software components on your microcontroller. So that's something where you need some tests. Yeah, you can try it out, but that's not a real test. It's not repeatable. It's not, you can only test the happy path and not the unhappy path. It's not automatable and things like that. Later, the HIL and the system test, HIL system test and system test are usually very late in the process. So that's also something that does not really help the developer in the early stages or during the most time of the development. So what we do with the miniHIL, we bring the hardware software integration test and part of the system test, big part or small part depending on the system, we bring it to the desktop of the developer. So while he's developing, he can run those tests on his desktop I'm going to show you later what this looks like. So that's the basic idea. So now let's think about what do we really want and need. We want to test what is changed most frequently. And that's not your hardware, that's your software. So you will not change your ECU or your microcontroller or whatever every 2 minutes or every 10 minutes or 15 minutes. You will change the hardware maybe at the beginning every couple of weeks, later every couple of months. But you will change your software during the whole process. So maybe sometimes, depending on your team size, 100 times a day, depending on the team size, of course, and on your project. So you want to test this. You do not have to test the hardware every time when you change a piece of software. That's very important here. Then you want to change. You want to test every code change for every developer, wherever he sits worldwide, within minutes instead of weeks. You want the full regression test also for unrelated code, because you might change something here and over there you create a side effect, a problem. And if you do not change the whole system, then you might run into a problem later, because you have only tested what you changed and not the side effects your changes might have. And that's especially hard in embedded systems, because they have shared resources, they have shared memory and things like that. So usually in embedded systems, that's even harder to do than or bigger problem than in a regular software system. You want the full test automation, especially for bigger projects or for more developers. You want to enforce the tests through continuous integration. So whenever somebody changes, any developer changes something, you want to run the tests automatically. It speeds up the development process, but it also enforces the test. So you always know that what's committed is tested. And last but not least, you need an automated hardware in the loop test to test more than pure software units, because it's not a pure software system. So you need to integrate somehow with the hardware to test. Now let's have a look at the different test levels and methods. Let's start at the system level. You might have a system level with an ECU, so electronic control unit, a motor, a pump, and a hydraulic system. For example, for a crane, a hydraulic crane, or for a lubrication pump, something like that, or water pump. That would be a very generic design for a pump system, for example. Actually, it's a very high-level design of one of our customer projects for a lubrication pump. So now we have the ECU, the electronic control unit. On the electronic control unit, you usually have power electronics, already some sensors, actuators, and things like that. Inside the ECU, you also have a microcontroller that controls your system, and the microcontroller has basically two software parts: the drivers to control the peripherals, so CAN, LIN, PWM, and so on, and the software. Software is what you develop, and now let's have a look at on which levels we can test what. So let's start with a pure unit test. Pure unit test tests a single C module or a single class. In the strict sense, that's a unit test. Usually you use the same test approach, a unit test system, also to make a software integration test. For example, if you bring some software units together, that's already a software integration test, but you can do it with a unit test tool. That's very good to do that, because it's fast, cheap. You can do it completely without hardware. It's completely automatable, so please do that. So the next level would be the microcontroller level. That's already a hardware-software integration test. So it's the smallest possible hardware in the loop test. You could also call this the processor in the loop test. So we test with the miniHIL, for example, we test the system at the pins of the microcontroller on a signal level. That's very important, because now we can simulate the complete environment. We can simulate the power electronics. We can simulate the sensors, the motor, the pump, the complete system. And by doing that, we can test already the complete software as it's delivered, including all the drivers. That's very important. So we do not have to modify the software. It's a black box test for the complete software on the microcontroller. Then the next level would be a big hardware in the loop test. We already have, for example, a motor attached to the system. You test the power electronics, sensors, actuators, and so on. And the last step would be a system test. So in the system test, you actually run the complete system, and that's usually really hard to automate. So let's have a look at the cost and at the cycles, development cycles. Unit tests you can run them very fast, very often, and they are relatively inexpensive if you do not overdo it. So please do not strive for 1000% of coverage or whatever it is. Now, of course, you will never. It gets really, really expensive if you have a very high code coverage. Let's say 100% MCDC or so. If you do not really need it, then that's very expensive. Huh? But certain coverage with unit tests is fast. You can run this often, and it's inexpensive. If you go to a big hardware in the loop test stand or a system test, that's usually very slow, very late in the process. You do not run this very often because it's really expensive. And the miniHIL is somewhere in the middle. It runs as fast as a unit test normally, so in the range of minutes. But it's relatively inexpensive in comparison to a system test. Of course, it's a bit more effort than a unit test. So as soon as hardware is integrated or in the test system, you have a bit more effort, of course. So, but it's somewhere in the middle, and it closes the gap. So those are the test levels. So the miniHIL is right in the middle of the test levels here. Now, why is it so hard to automate tests for embedded systems? Let's have a look at the typical motor control system for an oil pump, for a lubrication pump. Again, the same example. We have here, for example, in one system, we need to test all the temperature shutdowns, all the shutdown passes for all boundary values for 300 relevant system states. And that's a lot of test cases, and they are really slow if you run them in a climate chamber. So for example, this has been the old test system. They used the climate chamber for the complete test run, including the motor, the pump, the complete system. The problem was that the climate chamber is really slow. So let's say it takes 2 or 3 hours to get down from +40 to -40 degrees centigrade. And then suddenly something happens, like the oil gets frozen, or something doesn't work anymore. The mechanic has a problem, but you do not want to test this. You will only want to test the software changes you did, and this would have taken something like 30 days for all the system states and the shutdown passes and so on. And of course, it never ran completely. It ran maybe for a couple of hours, and then something happened and it did not continue to run. So it's really hard to automate this kind of test. And so it's not really used for software development. What we did in this case, we took our miniHIL approach. We took the real microcontroller with the complete motor control software and the drivers. We integrated it into our hardware software integration test with the test cases and environment simulation. And suddenly you get down, in this case, to 50 minutes for all tests, including all the other tests of the system. So not only the safety relevant tests. It's easy to automate, and you can also test all the bad passes, the unhappy passes, because you can make failure injection for the environment simulation. So you can break a motor. So it's hard to break a motor if it's attached to the system in hardware, because you need to cut a cable. In our case, it's relatively easy. It's just a piece of software that simulates the motor. So you can just set the signal to 0 or to a wrong value or something like that. So that's the basic idea. Now let's have a look at the typical response times. We said we want to test very fast. So at the lowest level, you usually have a component test, for example, a unit test or a software integration test on unit level. That's usually done within a couple of minutes for a normal embedded software. Then the hardware-software integration test is usually not done because there is not much equipment for that. So you might set up something for yourself, but that's usually hard to maintain. And then on system test level, simulated or on a real system test level, it's usually done every couple of weeks because it's really expensive and slow. And the acceptance tests are usually done on system test level, so they're also not very fast here. So now with the miniHIL, we close this gap and we get down with the hardware-software integration tests in the range of minutes. So usual test is a couple of minutes. If it's a slower system, maybe a couple of hours, but you can trigger this on every commit. So we have very fast turnarounds by automation, and you can run this within a couple of minutes instead of weeks, and we close the testing gap. Here you see the miniHIL, that's the size of a piece of paper. In this case, with an Oryx processor, the adapter has been done by Hitex for their customers. And yeah, we have adapters for all kinds of microcontrollers. And if not, we build they are really simple, those adapters, so that's not hard to do. Now, what can you do with such a hardware-software integration test? The main goal is not to test a single software component, for example, a motor controller or a battery controller or a bus protocol or something like that. You can test this, but you want to test the integration of the components into the complete software system, including all the drivers and electric signals. So by simulating the environment, you can put your system into almost any state to test it by changing the simulation for failure injection. And this allows you to test very fast through automation. You get speed, test depth, and so on in your test process. Now, let's have a look at an example. What can you test with this? I give you an example again, the shutdown path for the temperature I've mentioned before. Our black box is the microcontroller. So we simulate all the IOs here. For example, if you want to trigger the shutdown path, we make a failure injection by applying an analog value, a DAC, to the ADC with the temperature too high. Let's say 1.1 volt is a temperature that's too high. Then internally, because it's a black box test, the behavior cascades through your system. And in the end, what we want to know, because it's a safety critical system, we want to know, does the motor really shut down? So is the PWM really off after 100 microseconds? That's one thing I need to know. And the other thing I need to know here is, does the CAN message, the right CAN message, is this propagated to the CAN network? Because, for example, if it's built into a crane or into an oil rig, this pump, the crane needs to know that the lubrication pump does not work, because that's safety critical. If the lubrication does not work, the crane will fail with potentially catastrophic effects. So those are the two things we need to make sure that they happen. And that's something you can test on this level perfect. So how do we do this all together? Keep it as simple as possible. The miniHIL hardware platform is a relatively simple hardware platform with a lot of features, of course. Here on the right, you see that's a regular evaluation board of an STM32. You can just plug it on. If for many other processors, you can use an adapter we have, or we build a special adapter. That's not hard to do for any microcontroller. So the system under test is essentially this microcontroller, and we test it at the pins of this microcontroller. We connect the pins over this patch panel with our test system. That's the microcontroller of a test system. Why do we use a microcontroller here? Because we need hard real-time, because we want to run the simulation, environment simulation, and the test cases in hard real-time on this processor. What we do here is we simulate the hardware. So we have a virtual twin or an environment simulation, whatever you call it in your domain. By simulating this, we can bring the complete software on the system under test into any state we want, or into most states we want. Because, for example, if you do not have a motor attached on your system, it will fail immediately. It cannot even get to the state where you can test something, because when it is turned on, it will immediately run into this problem, and it will detect that the motor is not attached. So what we do is we simulate the motor over these cables, and then the processor can get to the state where it actually works. Typical IOs we can use is digital, analog, all the low-level bus systems, SPI, I2C, CAN, LIN, PWM, of course, mainly for motor control, but also for some protocols and so on, CentBus, etc. So there are a lot of interfaces you can use. So most interfaces those microcontroller use, you can simulate here very good. Now, you need three things on the test system. First of all, you need to bring the hardware signals into your test software. The second thing you need is environment simulation that simulates, for example, the motor or the battery or the CAN protocol that's attached to your system. And the third thing, you need test cases. The biggest effort at the beginning is usually to build the environment simulations. It's not as hard as it sounds. We have predefined simulators, for example, for motors and things like that. And in the end, once you have the simulators in place, you can easily create a new test case or create a new test on that level for a new product you have. If it has similar components, then you can reuse these components. So the effort gets lower and lower for your next projects. You can reuse those setups very good for the next project. Now, in order to do those simulation and those test cases, that's really hard to do if you would program it, for example, in plain C. That's not so easy to do because they are concurrent. They are running in parallel. They are asynchronous. So what we have here is a development environment, a model-based development environment. You can use it to define the structure and the behavior for your environment simulation, as well as for your test cases. And from those models, we generate C code. You also can integrate manual C code. You also can integrate, for example, generated Simulink models and from models from other tools. If you can generate it in C code, you can easily integrate this into your test system. Then we compile the C code. We flash it to this microcontroller here. And then we run it on this microcontroller. Why don't we use, for example, Python and run the test cases on a PC? Because we need really hard real-time on the test controller here. For example, to simulate motor control or motor, you need usually simulations between 20 and 40 kilohertz, something like that. And that's something you cannot run on a personal computer or on your laptop. So you need a deterministic hard real-time platform to run this. Now the tests run and the environment simulations run and stimulate your system under test and check whether everything is okay. Then we get the logs. While it's running, we get the logs and we transform the logs from the test cases into diagrams. The diagrams are really good because we as human beings understand diagrams, graphical diagrams, a lot better than a text log, for example. And we can create diagrams on various levels of abstraction. So low-level diagrams, what happens on I/O level, or high-level diagrams, how many features did I test with how many test cases, for example. Yeah. So what's my feature coverage? And then in the end, I learn and iterate. And this complete cycle is in the range of minutes. So it's really fast. You can run it on a desktop or on a continuous integration server. Now, something special. Since we already have modeling language for test cases, we also can model combinatorial test cases. They're called state transition tests. You define basically the black box behavior you expect, good or bad, for your system under test as a state chart. And then we take all the paths through your defined system behavior. So that's a redundant description of your behavior. So that's not your behavior in your system, that's the expected behavior in your test cases. And now we generate, for a certain metric, we generate all necessary test paths, test cases to cover a path coverage and a combinatorial path coverage and a combinatorial data coverage. And that's very good, especially if you want to test your system for robustness, for safety, for security. It's also a well-known test method, but there are not many tools that actually can really do it. So you can do it on a piece of paper, but if you generate 500,000 test cases, then you need a tooling for that. So that's a very nice thing to have, especially because you can detect many sporadic errors, race conditions. So those are errors that are really hard to find in your system. Now, that's what the hardware in the loop setup looks like on your desktop. So you have full access to all the pieces here, all the cables. And that would be a typical setup on your desktop, like I have here my laptop attached to the miniHIL system here. That's exactly what it looks like here. That's even my laptop here, I guess. So that's how you start. And then if your project gets bigger, if you have more people in the project, more programmers, more developers, or developers are distributed over several locations, then you might want continuous integration. Same thing, but with a big difference. Every code change that's committed or pushed to your server, to your Git repository, for example, is built, tested, and delivered. Here you see a rack with 19-inch rack, 1 meter high, with 8 different miniHIL projects. That's what it looks like if you have, let's say, 8 projects, or if you want to test your basic software for your system for various processors or whatever it is. So this runs on every commit. We have the same setup here in our office for the miniHIL product itself. So every commit is delivered with you. So with this setup, you can test every code change of every developer for every project, wherever the developer sits within minutes. So where do we use the miniHIL? We use it basically in all the domains you can imagine. So we have in all those domains customers. You see here, for example, one of our reference customers, Kercher, for industrial cleaning systems. They have a huge product lines with many different products, also in airbags, in cars, in motorbikes, and so on and so on. So basically everywhere where you have usually a 16 or 30-bit microcontroller. We also have projects with 8 or 64-bit microcontrollers. But the main point is, if you do not have any IOs, you don't need the miniHIL. But if you rely heavily on IOs like bus systems, motor control, and things like that, many cables, then you can use the miniHIL to test your system. Now, I'm giving you a little demo. That's the demo setup I have here on a logical level. We have the system under test. That's this here. That's STM32. That's the test system. System under test, STM32. Test system, also an STM32, a Cortex M7 microcontroller. And we run a motor control for a BLDC motor controller that uses 3 PWM. Generates 3 PWMs to control the speed of the motor. The motor simulation reads those PWMs and calculates the speed and returns the 3 Hall signals according to the speed, for example, your motor has as digital signals. Then we have a temperature sensor, here a DAC, an analog output, here an analog input, and in this case a UART to change the speed, to get error messages and so on, for communication mainly. So this could also be a CAN or a LIN bus or whatever it is you have. So that's the idea here. Then let's have a look at the electrical level. You don't need this view to run your test cases. It's just to show you a little bit what happens on an electrical level while a test case runs. That's the PWM output for the motor. On this side, we have the miniHIL. The miniHIL generates the whole signals as digital outputs, for example, with 120 degrees, or maybe 119, 120, 121 degrees, depending on what your motor delivers. Then we have the UART here. That's, by the way, a normal Saleh standard product logic analyzer. And here, if you zoom out a little bit more, then you have again the 3 PWMs here, the whole signals, the UART communication, and here the simulated temperature. Here you can see the equivalency classes and the boundary values for all the temperatures, the good and the bad temperatures, yeah, too high, too low, and so on. And that's just the current speed of the motor simulation. To get a correlation between your test cases and the behavior of the simulation and the behavior of application. For that, this kind of information is really useful. It's not really needed for the test automation, but for us to analyze it later, what happened here. So for example, if we want to test a speed change, we send a package with a new speed. Then the motor controller changes the speed. You can see this, the PWM gets slower. And then this motor simulation follows. It's a real closed loop simulation. And so the simulation gets slower. Then we have a mode full stop for the motor temperature error. That's what I told you before. Here I want to know whether for example, the PWM is off for more than, I don't know, 10 seconds or a second or whatever it is. Then we have a recovery behavior, then a temperature warning. The temperature is only a warning temperature, so the motor gets slower a little bit to recover. And here we have the recovery. So those are typical test cases we can run and combine with all the other things you want to know of your system. Now let's have a look at the demo. So I just give you a brief overview of our modeling system here. That's a model, that's the complete model of my example here. We have down here, we have the I/O adapters. So analog, digital, UART, the whole generator, the duty capture unit for the PWMs. And for example, we measure the PWMs 20,000 times a second or something like that, or 20 kilohertz. Then we feed them into the motor simulation. This can be a C code. This can be a modeled state machine. In this case, that's a state machine. It's a fully functional state machine editor. We can directly generate the code from this. We can integrate it also with C code if you have some manual C code you want to call there. And then then it sets the whole gen out port. It sets the speed for the whole generator, and the whole generator is again a piece of software that controls the 3 digital outputs for the whole generation. Here the motor temperature simulation, so that's the simulation level here. And in the end, you need some test cases. And of course, that's a simple demo system. If it gets more complex, you can build hierarchies. So I'm zooming in or I'm going into. You can decompose and compose components to more complex systems or to simpler systems. And in the end, you have a test case here. And the test case is also modeled. By the way, all the languages are textual languages. That's very important. So you see this graphical language here, but in the background, you always have a textual language. That's important. You can diff it, you can merge it, you can reuse it, you can commit it. So it works basically like a piece of C or Java code, but it's a high-level abstraction for your test system. And that's very important because you want to reuse your test systems. You want to diff them, merge them, work on branches. You want to check the test system in with your project. So whenever you branch your project, you want to branch your test cases as well. And that's really easy to do because it's just a piece of code. Yeah. So model as code or code as model, basically. Now here we have the test cases. Again, it's a textual language, but the textual language, we generate directly graphical diagrams from it. So for example, if I click here on the sequence, you get the diagram for the sequence. I click on a single step. Here you see the diagram for a step. Sequence diagram, that's easy to translate here in this case. So in this case, we would not need a diagram, but for example, for a complete test suite, it's really helpful to see all the test cases and how they relate to each other. That's important because you want to see the context. So for example, when here something fails, you want to see what happened before. So now that's how we model the test cases and the environment simulations. Now you can generate this, compile this, flash this, and so on. And then you can either run it directly from here, from the development environment, or just connect a little graphical user interface to it. So for example, if I'm working on my application and I just want to run the regression test, you just click here the regression test button. And now while the test is running, I'm pulling a plug here. So now I created some errors. That was the UART, I guess. And now you see those tests failed. Here you see the combinatorial tests. And here you see, for example, this test case failed. That's the test that failed. And now if I click on the reason why it failed here, see, it's the same diagram I've shown you before. Before that was the expected behavior, and now that's the real behavior that's been logged during the test case. I click on the timeout here, and in the IDE, it jumps directly to the right step. Here, that's the step request speed, and shows me exactly where it failed. So this reaction did not happen. You see that's missing. It ran in a timeout after the send done. So that's as close as you get. And you also can run this on a continuous integration server. For example, that's a Jenkins server. I can directly hook it up to the Git repository. And whenever I change something, the continuous integration server starts. And here I also get the same diagrams I have on the local system. So you can also, it's always the same system you're running. Okay, so that's the demo so far. I hope you enjoyed the presentation, and if you have any questions, please don't hesitate to contact us, either Michael Weiss from Hitex or me directly from PROTOS. We can discuss your use cases, or if any questions, just send us an email and ask us.